Hi, everybody in Research Methods Psych 290. Today, we're going to cover two topics, which are both relatively short, and that is why we're going to cover them in the same day. But yet, a second reason is they really do relate well to each other. The first one, section 11, the null hypothesis and rejecting the null, it can honestly be very confusing. In fact, when I did my PhD, we spent a couple of weeks kind of dissecting this topic, and the more we talked about it, the more confused I was. So I'm going to try to keep it simple for you. This is only an undergraduate class, and just tell you as much as you need to know to do well on the exam about this particular topic. So here's the basic idea. The null hypothesis is rarely something that you would put in a research report, but it is something that you test statistically. It's an assumption that something is unchanged, that two variables are not statistically related to each other, that there is no statistically significant difference before and after something happens. Basically, the null hypothesis is that there is no significant difference. So, if we were all on campus together and we tested each of the soda and vending machines that are usually having snacks in them, we might start with the assumption that there is no difference. But if we walked all around campus, we might find that there is a difference that we didn't expect. So, you test the null hypothesis, but usually what you're stating in your paper is something called the alternate hypothesis. These are symbols here, H0, and you will see H1 coming up here in a little bit, and those are the symbols. Did I tell you it was confusing? I sure think it is, but again, I'm going to try to keep it simple. So by the way, with a hypothesis, we usually state it in the future tense. We have not yet done the research, so the null hypothesis says there will be no significant difference between two variables before and after something occurs. There will be no significant correlation if that's what your study is about. So that is what you are testing. But the first confusing part is that's not usually what you're reporting in your paper. Usually what you're assuming is that there is a difference, or that two things are significantly related, or that there will be a difference before and after something, statistically significant, that is. Is there ever a time that a researcher predicts no difference? Sure, I could think of a couple of examples. Maybe a new generic medicine is made, and you're assuming that it will be no different than the one that costs a lot of money. Well, there's an example. But again, those things are unusual. Usually we want to predict that something is newer, better, different, changed. So again, the null hypothesis is H0. That's the symbol for it. Oh, look at that. Another hole punch through a word that we need. Alpha. So, getting alpha. What we study in psychology most of the time, an alpha level or a significance level, A for alpha, 0.05. That is the most common criteria we use. What does that mean? That there is a tail of a normal curve, and we are predicting that the significance falls into a tail. So in other words, I want to be no more than 5% chance of error, 5% room for error, you could say, 95% certain, that's the remainder of it, that would be your alpha level. So then I would run my statistics, in this case a t-test, and if it comes out to 0.04 or 0.03 or 0.02, then I would say I reject the null. The null was a statement saying there will be no significant difference. But if I can get an alpha level equal to or below that, then I would say I reject the null because there is a significant difference, but I could also say that I accepted the alternate hypothesis, the H1. Did I tell you this is confusing? It is. Now, is there ever a time that being 95% certain isn't good enough? I want to be even more sure than that. I want to leave less than 5% room for error. I could think of plenty of examples when a researcher would want to have no more than 1% room for error, 99% certainty at least, or 0.001, 99.9% certain, no more than 0.1% room for error. You could even go beyond that, 99.99, 99.999, so on and so forth. How certain do you need to be, or do you want to be? But again, in psychology, the one we use most often, because we're not talking about life and death usually, 0.05. What might be some exceptions where you need to be even more certain, like 0.01 or 001? Well, what if you're testing a life-saving medication? What if it's seatbelts or child safety restraints? What if it is the safety of a bridge? Wait a minute, what if it's birth control? Would you buy birth control that said 73% effective? I don't think most people would. So it is the alpha level of how certain we want to be. But once you run your statistics, you will get what's called a p-value. And you'll see that as soon as you start to crunch the numbers, first with the practice numbers, and then with your numbers from your surveys, you will see that it really does compare the p-value that you are given compared to your alpha level. So for example, if I want to look at male-female differences and I do all my numbers, put in all my survey scores, and it's p equals 0.03, that's lower than the 0.05 that I had as my alpha level. So I would say that I am rejecting the null. The null is an assumption that there will be no statistically significant differences. So this is confusing. I'm the first one to admit it. Just try to follow along and do your best, and I think you'll be fine. I don't want to make anybody stress about this too much. So moving right along, we're going to have a few examples here in a minute. It talks about how if the p-value is greater than 0.05 in most psychology experiments, then we fail to reject the null. In other words, we say that the null is accepted or retained. There's a couple of different ways to say that. But remember, your hypothesis is probably that there is a difference or there will be a difference. So if I'm predicting male-female differences, that's what I want my hypothesis to show. So I'm kind of hoping that p will be less than 0.05 here, because that would tell me that I can reject the null and that there is a statistically significant difference. Moving right along, I am going to turn this around here. So I can rotate it. There we go, counterclockwise. This is the end of this chapter. Then we're going to move on to the next one. Type 1 and Type 2 error. If that wasn't confusing enough, what we just talked about, it now gets a little more confusing, but I'm going to try to keep this as simple as possible. You're the experimenter, right here. This is you, the experimenter. What did you decide? To retain the null. This is a statement right here saying there will be no significant difference. And what I found in my data, yep, there is no significant difference, at least not statistically, maybe between males and females. I retain the null. But this one says I reject the null, and that would mean that you do accept the H1. So rejecting the null, I The null said there will be no significant difference, and I found that there was. Wow, in this case, maybe males and females really are statistically significantly different than each other. Now, you ready for it to get a little more complicated, even more? What if your decision was right or wrong? We're talking now about the actual situation. What if you later learn something different? Now, remember, let's start here in this bottom right-hand corner box. You retained the null because after you did your statistics, you found that males and females, let's say, are not significantly different. But wait a minute, what if the null is false? In reality, there is an effect. What happened? Why were you wrong? Because you used too small of samples. Maybe you only had 7 people in one group and 8 people in the other, and had you used more people, it would have been statistically significant. So see, samples too small. All you need to know for the exam, make yourself a little note like I did with my messy handwriting here. How does that happen, a type 2 error? You didn't use enough people. Samples were too small. What about the opposite problem? You reject the null hypothesis and you make the assumption based on your data that the two groups are different than each other. Perhaps males and females are different based on your result. But wait a minute. You later learn that there's no true effect and that the null was actually true? How did that happen? Well, right here, you had a biased sample, or maybe even both samples were biased. What does that mean? Well, maybe all of your males were just average students and all of your females were honor students. No wonder why library usage is so different, because you had a biased group of students with so many females being in the honors program. So again, I apologize that this is perhaps more confusing than you would have liked. I find it confusing too. I try to simplify it as much as possible. Moving right along, we are now going to go to a different page, or a different section, I should say, of the reading packet, and that would be section 12. So, give me a minute. There we go. Section 12, percentages, percentiles, and the normal curve. If we were in class together, we would talk about both of these things on the same day. So here we go. If you read Webster's dictionary, it is confusing, but in a different way than the previous section was. It's just similar wording. Percentage is something out of 100. Whereas percentile, yes, it's also something out of 100, but it's more in relation to how you compare to other people. So, if you got an 83 on the exam and there were 100 points possible, well, that's pretty easy math. You got an 83% or percentage. But if you happen to do better than 83% of all people in a study, or in a large lecture hall, that's percentile. So percentage is how did you score compared to a possible 100. It's an easy frame of reference to use 100 as a benchmark. But percentile, how do you compare to other people? So, in most of your college classes, it's all about percentage, not percentile. You usually don't have to worry how you compare to other people. That's not usually how your grade is set. There is some exceptions to that, though, or are some exceptions, like law school. Your percentile matters. It really matters how you compare to other people. So being competitive would be a good thing in law school. But in most college classes, it's about percentage. Have you ever had a job where you had to compete with other people for sales? Well, you're talking about percentile, aren't you? How did you compare to other people? They might even say you're in the top 10% of this company. They're really talking about percentile. But Did you meet your goal? You were supposed to sell 300 items and you sold 270? Well, you sold 90% of your goal. And maybe that's a good thing or maybe not. So that's how percentage and percentile are different than each other. When it comes to percentile, there is a normal curve. Not always, but quite often, where an equal number of people are below average and above average. When you're talking about sales or when it comes to academic performance, it's often put into a normal curve so that you can compare people to each other to see how above average you are or below average you are. The central limit theorem says that the more samples that you take, or even the bigger the sample is that you take, the more it will represent the normal curve. So if you just take a few people or a few small samples, that does not necessarily approximate a normal curve. But the bigger the sample, the better. So let's move right along here. Two things I want you to know. This will be on the test. There is no 0th and there is no 100th percentile. People use those terms incorrectly. Somebody might say to you, oh, my kid is so smart, he's in the 100th percentile. You can correct that person and say, no, your son could be in the 99.99 percentile, but you can't be better than yourself. If you are part of the group that's being compared, then you're not above everyone. Same thing on the bottom end. 1 percentile, maybe. 0.0001, that's even possible. But you're not in the 0th percentile. There's no such thing. That's kind of a myth that a lot of people don't understand. So no matter how smart you are or how rich you are or whatever, how strong you are, you're not in the 100th percentile, nor are you in the 0th percentile. If you are part of the group that you're talking about, then you're somewhere in between. Is that a little confusing? Maybe, but I think it makes some sense. Then the last thing is, let me turn this around again. I am going to rotate it. Let me do that again. Rotate again. And one more. Should have started the other way. This is not something that I would try to memorize. It's just to be able to visualize. Where would you be with a percentile when it's a normal curve? Again, the central limit theorem says the more samples you take or the bigger the sample, the more it will approximate a normal curve of the population. This top one here shows the actual curve and the percentage of people that fit into the percentile. Right below uses a standard deviation of 15 points. That's how IQs are measured. So do you see here how a person with an IQ of 130 is 2 standard deviations above average, and there's really slightly more than 2% of all people who fit into that? The same thing would be true for 2 standard deviations below average, an IQ below 70. And that also means that a little more than 2% of people would fit into that. Where are most people? Average. The average person is very average. They would fit into the middle. Do you want to know exact numbers of percentile rank? Well, right here, they give you approximations of that. Do you see how the further you get away from average, the more rare it becomes? Stanines. This is commonly used in elementary school testing. They don't want parents to freak out that your kid is in stanine number 3 or number 8, so it kind of sounds less threatening than if they tell you the exact percentile. We usually save that more for adult testing. Normal curve equivalency, kind of the same thing, but broken down by tens. Again, just different ways to represent the same data. All of this is really very similar. It's just different ways of representing pretty much the same thing. So we covered 2 chapters in the reading packet today, didn't we? This was number 12, and before that we did number 11, and that is where we are going to leave it off here. Take care.